the morning session. This is by Professor Tuhin Roy from TIFR Mumbai, and he's going to talk about Higgs boson in BSM scenarios. So about Professor Tuhin Roy, he did his PhD from Boston University, followed by postdocs from University of Oregon and University of Washington at Seattle. And then he was a director's fellow at Los Alamos National Laboratory, and then joined TIFR as faculty in 2014. And his research interests are mostly collider physics. And to him, and it's over to you, and we'll keep your talks about 50 to 55 minutes, and followed by questions. Unless there is some pressing questions, let's wait till Tuhin finishes the talk. Of course, we can allow participants to in the middle to ask questions if there is a pressing one. Tuhin, up to you. Thank you.
Can you hear me?
Yes, yes. Somehow you are a little bit. Yeah, it's not clear.
Not recording at your end. We are having some problem here. Okay,
is this better?
Yeah, yeah, much better.
Okay. If you have trouble, just let me know. Hearing me, I think time and again my speaker system doesn't quite work.
Sure.
One second. How do I record? Okay.
Yeah, fine, good. Thank you.
All right, so let me start. So first of all, thanks a lot for inviting me to give this talk. So what I understood, so the title that Kajari assigned me was that the Higgs in BSM theories. Now, if this conference was more contemporary, but conference not this having this nostalgic tune about what's happened last 10 years or how we came to Higgs and so on, I probably have given a very different talk, because the way we think of Higgs in the context of BSM is slightly different from how we have been thinking for the past 20 years. So let me just summarize how, if we last 3-4 decades of thinking of BSM theories in the context of Higgs, or Higgs in the context of BSM theories, I basically have a cartoon to show. So in today's world, you think Higgs to be a part of the BSM, a small part of the BSM, things that you would like to think of. But the way we have grown up, the way I've understood is that you like to think of BSM via a lens of Higgs, because you want to have, we thought that there's a strong indication that there exists BSM, and the reason has to do something with Higgs. So it was literally pulling an elephant by its tail, was that is via Higgs, we thought we are going to understand that deeper structure of nature, and that's quote unquote BSM. Okay, so the talk is going to be in this tune, is that I'm going to talk about why and how the BSM works when you think via the lens of Higgs. Okay, now the first warning, I was also instructed that the talk should be intended for students. So what it means that I had to tone down significantly and explain the concepts, and that was been 55 minutes talk. For the initiated ones, this might be a bombardment on your intellectual self. So if you get bored, just go have some coffee. There are more serious talks to follow. Okay. The second thing is, what I was going to say is that there are many people who are going to cover this topic of what the current status is, reach is, and so on, for future experiments and so on. So I was not going to talk about it. I'm simply going to talk about how our understanding of BSM developed or worked out as we look through the lens of Higgs. Okay, and then finally, as I said, this is going to be based on my personal understanding, so it's going to be biased and opinionated, and I will omit a lot of things. I apologize in advance. Okay. All right, let me start. So first, let's fix the notation. So throughout this, when I refer to by Q, I mean an electroweak doublet. So it has left-handed up type and left-handed down type, and so on, charm and straight. So okay. So U and D, when I roughly refer, those would mean the right-handed ones in the different generations. By L, I would simply mean the left-not doublet. The capital H I would refer to as the Higgs doublet, and the small h is the 125 GeV guy. Okay, so that sort of fixes the notation for me. So as I said, so this is the meaning of the talk was I was trying to say is that why and how of BSM via Higgs. So let me just start and give this rough understanding of the scales in zoo of particle physics, right? So you have this absolutely massless photon, and you have an incredibly heavy top at 175 GeV. In between, you have neutrino masses of few electron volt or maybe lower. Don't quite completely know the picture. Electron appears at half an MeV. The muon, pions, kaons all are quite close to each other. Then appears rho, proton, neutrons, and so on. Electroweak gauge bosons and Higgs quite close, 100 GeV, 125 GeV, and so on. And then there is the top, right? So once these scales are given, the first thing that you try to think of is what are the origins of this scale? Are there all those fundamental scales, or they are derived from the fundamental scales? Okay, so here is the explanation of some of them using formulas. Like your electroweak gauge bosons is actually related to electroweak scale multiplied by the electroweak couplings. Higgs mass is again related to electroweak scale multiplied by a quartic coupling, a dimension less coupling constant. The fermion masses are all related to the electroweak scale and the dimension net coupling constant. Proton mass, that's the QCD scale. Okay, pi square is the pi mass is quite exotic in a sense that it has the dependence on the QCD scale. It is also sensitive to the Yukawa coupling and the electroweak scale. Right? You could see that if I take the Yukawa coupling or the electroweak scale to 0, the pi square simply mass vanishes. The neutrino masses, even though we have some understanding of maybe where they are, but we have so far no clue of the nature of the neutrino masses, whether it requires a fundamental scale different from the scales which are already present or not, is not really settled. Okay, so that's the story. Now the reason I tell you this is because as you go back between all the different scales that you observe in nature, and you think of what the origin is, and you realize that there are two fundamental scales in my theory. The reason I still wrote here mu because the neutrino is not quite settled as of yet. So you have these two scales, electroweak scale 100 GeV and the QCD scale 1 GeV. Okay, and then there's a hierarchy of 100, and you know that Higgs is extremely important in the sense that if no sources of separate electroweak symmetry would have been there, then your W and Z masses would have been at the scale of QCD. Okay, because QCD does the electroweak symmetry on its own. Okay, so it would have given masses. The fermion masses requires more constructions, even if you can make them massive, but that would involve something more. Okay, but the main point of what I was trying to get through here is that indeed there are two independent scales in our understanding. That's the electroweak scale and lambda QCD. All the other scale that you see is simply derived by various dimensionless coupling constants multiplying these two fundamental scales. Okay, that seems to be roughly the world of particle physics. That's how it's working. Okay, so let me ask the question. Okay, these two are the fundamental scale. Why don't we seek out the origin of these two scales? Okay. Now you may say, why do I care? Right? I can go on doing experiments, and like an explorer, I only think about things which I can't explain and things like that. Why do you seek out questions which are difficult to answer and may not even have a good solid answer? The reason you want to do that, or some of us want to do that, is because if you try to seek out the meaning of these stories, you may be, say you will not guarantee, but you may be able to find some fundamental principle which will give you an understanding of how nature works, how the creator works in terms of creating this zoo of particles and the world. Okay, so you're looking into the deeper understanding of all the scales, of the physics is. Okay, so let me start with the QCD scale. Now it turns out one of the most beautiful theory that you could ever come up with. In terms of, when you look at the QCD at very high scale, it's actually a scaleless theory. It doesn't really have a scale, at least classically. What happens when you take into account quantum mechanics, you realize that it is not quite scaleless. It has scaling, in fact. And as a result of which, even though it is characterized by a dimensionless coupling constant, alpha strong, that itself makes it, the quantum correction makes it change alpha as you go to a larger and larger distance. Okay. As you keep on going at larger and larger distance, at some point the theory becomes strongly coupled. And as it happens, in QCD's case, as we observe that QCD becomes strongly coupled, it confines, we actually get bound states on all those cases. As I said, it can even break down electroweak symmetry and so on like that. So, but the way that we gauge this QCD scale, starting out with a very, very, let's say, high scale theory where there is no scale, only had a coupling constant given as alpha is 0, is that the low energy alpha QCD is given as that input scale where you started out with, and this enormous separation of -4 pi alpha is now. Right? This is called dimensional transportation. It's well understood. Okay, people love this phenomena, and that's one of the reasons why we say that the QCD is probably the most beautiful part of nature in terms of describing the world. Okay. So QCD is well understood, as I said. The main thing that you learn from here, that the generation of QCD scale is a purely quantum mechanical effect. Okay. So now come to the electroweak scale. And as it turns out, the dumbest way to get an electroweak scale is actually what nature prefers. In terms of, you could write down a classical theory, like what I have written. I'm pretty sure you have seen that in zillions of times, with a quadratic term and a quartic term. And if mu h squared is negative, then you see that the potential is minimized at a particular scale. It's again given by the size of the quadratic term that was present. Okay. So if you want this to minimize our order 100 GeV squared, you expect mu h squared also to be 100 GeV squared. Okay. This is before, as I said, this is the dumbest way to do this thing, and that ends up being what nature has chosen. Now the question is that it's still a classical picture, and we haven't thought about when you apply quantum mechanics to it, what happens to it. And it turns out the issues are very subtle, and issues are so subtle that you still have fights over coffee mugs in the canteen. Okay, so let me start giving you, as I said, it's intended more for students. So what I'm going to do is that I'm going to explain this phenomenon of UV sensitivity in a simple calculation, in a toy model calculation. Okay, and we'll take it from there. So here's the toy calculation. What is it? So it's a model of two scales. Okay, it's as I have observed in nature, there is a scalar at mass ml, which I have observed over there, a fermion at mass mh that I have observed over there, and let's imagine they put an interaction in which looks like a Yukawa-like interaction. Okay, now it's straightforward to write down the Lagrangian. That's my Lagrangian for the free fermion. This is the Lagrangian for my free scalar, and this is one interaction that I said exists, and I will test that model in some ways. This seems to be trivial. So if you just give me this Lagrangian, I would say, well, why have you written UL square over here? It's a Lagrangian parameter. I should simply put ML square at this part and settle with it. But as I said, it's a classical theory. I need to calculate the quantum mechanics. So when I try to do the quantum mechanics, then those dreaded aspects of quantum field theory comes in, that there are divergences. We know exactly how to tackle them. And what we need to do, we just simply need to write down the counter terms. Okay, counter terms that take care of the divergences, the infinities that arises at very, very short distance. Okay, so we do that. So I wrote the counter terms. Delta S squared looks just like the kinetic term. Then S squared, which exactly looks like my mass term. Okay, this delta mu and delta S are two unknown parameters that order by order in perturbation one can take care of to determine that, to make sure that I get the right answer. Okay, but let's do it just only at at first order imperturbation theory, and then try to see that at first order what value we get in delta S and delta V. Okay. So how do we determine that? You determine that by looking at the 2-point functions, which has these 2 external legs. The way we describe 2-point function, we think all of them are incoming momentum, but that's okay for now. We basically looked at the 2-point function involving the scalar, okay, and we want to make sure it is divergence free at all steps, okay, and we will ensure that by choosing my delta S and delta V, right? Okay, so at one loop, you get the diagram where there are the scalars and these are the fermions. The fermion gives you a loop. And now since you have added the counter terms, here is that extra term that also contributes. Okay. So I evaluate the loop over here. It looks like a very, very complicated thing. But since it's infinity, I need to regulate it. I chose the dimensional regularization. That means I have evaluated it at a dimension d, which is slightly less than 4. Okay. So epsilon goes to 0 limit when I reach my d equals to 4 calculation, the honest to God result. But as you see, as epsilon goes to 0, I have captured the way the infinities occur. Okay, as epsilon goes to 0, this is where the infinities come, and this is a nicely way that I have said that captured as small value of epsilon, how the infinities show. Okay, so this is what the contribution is. Now, what I do here, I have chosen the MS bar scheme. What as it does, it just gets rid of the divergences. So delta S goes away. I determine to be y square by 4 pi square epsilon. This is over here, and delta mu to be that such that this 2-point function is divergence free. It doesn't have 1 over epsilon business in it, right? Now, if I do this, then I demand that the pole of this 2-point function exactly occurs where I have observed, where my experimental friend have given. So then you realize that the Lagrangian parameter that I need to put in, that's the mu L square, is ml square, where the pole appears, times this factor y square by 24 pi square, but then there is this 6 mh square. Now remember what mh is. mh was the mass of the heavy fermion, okay, which I can decouple if I want, and I can push it up and down. And the worry over here is that the lower mass of my the Lagrangian parameter that I'm going to put over here, right? This has a dependency on that heavy mass. Okay. Now, this is what is strictly speaking defined as the UV sensitivity of the scalar mass. Okay. Of course, it's a scheme dependent story, how much exactly that you put in. But the fact that even in scheme dependence, you actually see that the number that you're going to put in your Lagrangian is, it depends on the arbitrary high scale. That is, that unusual nature, what you don't expect is what is called the UV sensitivity. Okay. Now, in the context of the Higgs, before I actually go to the context of the Higgs, let me bring out something that we know in nature. Okay. How does the UV sensitivity shows up? For example, in a slightly different calculation. In the calculation of the measurement of the calculation of what the pion mass is, what the charge pion mass is. Okay. Now it turns out that at tree level, when you write down the Lagrangian to very, very good approximation, right? There is a symmetry in the tube at very low energy, and that symmetry is called the isospin symmetry. And the pions, pi naught and the pi plus, pi minus, these two form a triplet under that symmetry. Okay. So the prediction at tree level is that your pi plus and pi naught are exactly the same. They have exactly the same. It turns out that the symmetry is broken by electromagnetism, but electromagnetism contributes to the mass of pi plus. It doesn't contribute to the mass of pi naught because pi naught has no electric charge. Okay, it contributes to the mass and it gives you a splitting. Okay, so I took the diagram to calculate what the splitting is, and it turns out, if I naively I estimate to be squared, lambda squared over 16 pi squared. Lambda is supposed to be the cutoff of my theory. What is the cutoff? Cutoff is the theory is that, you know, in my theory I have not included any new resonance. So the cutoff of my theory is the one that I include new resonance and so on. So the new resonance shows up at the rho mass. So if you put it m rho squared, you roughly get the right number. Okay. Now the thing is, here everything is well defined. In terms of m pi squared is what you measure. In terms of m pi naught squared is also something it measures. And this is what you are putting into m rho squared. So everything is some sort of you can check. Okay. If you import this idea of what you are seeing over here into Higgs sector, then similar thing follows, but the result is not as crisp. Okay, and that's what gives rise to much more stability. So let me just do over there. So if there exists a cutoff, let's say there exists a heavy resonance that you haven't yet seen. Let me call it again rho with a mass of capital M rho. Then by the same logic as before, you should expect that this mu squared h parameter at one loop, this is equals to the mu squared h parameter at 3 times the contribution of the, let's say, the top loop, and you are supposed to get yt squared m rho squared over 8 squared. Okay, this is large if m rho is large. Left hand side, we know that it is ordered 100 GeV squared. Okay. This guy, imagine that m rho exists at very high scale, then this contribution is also pretty large. But to be honest, it's not a similar contribution because I don't have any understanding of what this mu squared h at 3 level is. Okay. So it might very well be very large, such that it stops that calculation at the end of the day and gives you this one, the right number at 100 GeV squared. So great. Now the question is that, do I have a problem? Okay, as I said, the answer to that question is not really straightforward. It depends on your outlook, it depends on your experience, depends on how you think about physics. Part of the reason is because if I have to do a cancellation of 10 to the power minus 18 minus 10 to the power minus, sorry, 10 to the power 18 minus 10 to the power 18 to get a factor of 1, is that a problem or not? I'll let you decide that. Okay, and I'll come to that some sort of different answer towards the end. But let me leave here and say, this is where the thing is. This is what creates a lot of storm in canteen areas in various research institutes. Okay, good. So let me go to the second problem, and I just stop over here talking about the problems. So the mass of the, as I said, I hand wave and I say mass of top is pi top times B electroweak. Rajiv, you have a question. Can you wait a bit later?
Okay.
All right. Okay, and the uptype is again y up V electroweak by square root of 2. Okay, so you could ask the question is why top is so much heavy compared to uptype. It's order 10 to the power 5 number, which is basically tells you sum of your dimensionless coupling is 10 to the power 5 bigger times the other dimensionless coupling. Now, there seems to be a hierarchy in the Higgs coupling itself. Okay, and you could ask the question, do I have a problem? Right? So let me stop over here and let me not summarize many problems because I will not be able to go through this. And let me try to give a different type of, let me avoid giving an answer to this problem. Okay. So if you don't have a problem, you don't have a problem. That's good. But if you call yourself naturalist in a sense that if your belief system says that I don't like large cancellations, okay, and you want to say like my dimension full numbers, if they're very small, I need to have a good reason for them to be small. If this is your belief system, this is whom I would call you a naturalist. Then obviously, then you have a problem. It turned out that we took this naturalist viewpoint very, very seriously for a really long time. Okay, what happened because of that is that we realized that there is a problem, and so people have this gives us, it made us the guiding principle. There was a guiding principle towards understanding what physics exists at a very, very short distance. Okay, and any time of the day I will take a word with a guiding system towards understanding fundamental knowledge, then just wait here on my chair and try to find anomalies. Okay, but again, that's personal thing. But on the part, the good front of it, that because it gave us this guiding principle, it has given rise to enormous amount of intellectual development. Okay, people found creative ideas to try to solve this problem. Okay, and as I said, model building phenomenology, this is what dictated. Okay, this taught us what we expect for the BSM physics, and one of the great things that happened because of that, it also made us ready about if BSM shows up, how to find it. In terms of when we ran LHC, we were ready, how to find different things, because all those different ideas prepared us what to expect. And if you know what to expect, you can do your simulation, you can be ready, and that has helped in our the experimental code as well. Okay. Now, as I said, there are many creative ideas. Some employ symmetries, some employ lowering the cutoff, some employ anthropics, many ideas. But let me stick with symmetries, right? It's not just I like to talk about it, but it's one of the dominant stream in our research, okay, in many decades. Okay, so first let me go to supersymmetry and let me blitz it through but try to be in a transparent manner. So what does supersymmetry do? It tells you that it's a larger symmetry that incorporates scalar and fermion together. Okay, and the algebra basically tells you that in fully supersymmetric theory, the scalars and fermions who transforms into each other, they have the same mass, which is a wonderful thing, because the fermion masses are a wonderful thing as opposed to the scalar masses. Let me explain you why. So this is the Lagrangian that I wrote here, is your extremely traditional Lagrangian of, the free Lagrangian of, let's say, Dirac fermion. The moment you take MF goes to zero limit, you find an extra symmetry. So it's a symmetry under which the top component and the bottom component goes in a different direction of a Dirac fermion. Okay. So this is the chiral symmetry, and your Lagrangian becomes recovers an extra symmetry. So this just tells you, since I have an extra symmetry in the MF goes to zero limit, even after I take quantum corrections into account, I should still have the symmetry intact. That just tells you the correction to the MF, even if I started MF equal to zero, it should remain zero. Right? Clear? That if I take MF goes to zero limit, I recover an extra symmetry. The extra symmetry tells me that in this limit, even after quantum correction is taken into account, I still have the symmetry left over, and thus tells me the quantum corrected mass still remains. Okay. That allows you to extend this idea to say that, so therefore, since it's a violation of that particular symmetry, the quantum correction to the amount of violation should also be proportional to violation itself. So delta MF should be proportional to MF. Okay. So that's right, because supersymmetry tells you correction to the scalar mass should be equal to the correction to the fermion mass. Correction to the fermion mass is proportional to fermion mass itself, which is equal to my scalar mass, and so that simply tells me that the correction to my scalar mass is proportional to scalar mass itself, right? So supersymmetry, you can say that in a sense that supersymmetry has rotated chirality into the scalar sense. Okay. It's extremely beautiful story. But as we know, all of you heard that we have not found any shred of supersymmetry, so it has to be broken. And does this beautiful relationship gets preserved, right? And that depends on how you break it, right? And there are, there are three different ways that can get resulted. In one case, you break it in a what I call a hard manner, but then you see that you again become sensitive to your cutoff. What we call the soft manner is that your cutoff shows up only as a logarithmic way, and you still, the MF tilde square, which is the splitting between the fermion and the scalar mass, that becomes again proportional to the fermion and the scalar mass. So the MF tilde square is proportional to MF tilde square, but the UV scale still shows up as a logarithmic way. Those are called soft. Okay. And then there's a super soft, which doesn't even have the log dependence. Okay. So the soft place is what we love most, in a sense that most of the phenomenologists and experimentalists have worked in many years. the minimal of the construction is the MSSM, and that's what we talked about. Okay, so one more slide about Sushi. So the title of the slide is that people who love Sushi, why do they love Sushi? Okay. So the one of the reason is that it provides an enormous amount of phenomenology, as I said, which is interesting. We can think of many possible ways how to decode signals and so on, and that's one of the reasons people love it. And if you are fond of thinking of what do we see, whether there's an elegance to it or not, and how it works, then yes, people like to use that word, that it's a beautiful theory if you think deeply about it. And there is also an additional thing, that the advantage of having the supersymmetry built in, but some way of having a tactable this supersymmetry breaking parameter, it allows us to calculate it in an extremely precision manner, because there exist many results in supersymmetric theory which you can use, okay, just for the sake of calculation. Okay. So as I said, these are the model builders dream world, okay, and that's part of the reason why many of us worked and so on like that. Okay. So last slide about supersymmetry. How does the Sushi phenomenology differ? You have heard it millions of times so far. Let me just say it in one sentence, 1 minute. The Higgs sector is extended to a 2HDM. Okay, so that means 8 degrees of freedom, out of which 3 are eaten. So you get the 5 real scalar degrees of freedom. One of them is our 125 guy, and the rest are 2 charged guys, 1 heavy scalar, and 1 pseudoscalar. Okay. Apart from that, you also get gauginos like gluinos, vino, xeno. These are all superpartners, fermions, quarks, etc. Gluinos and the squarks are the colored guys. So they're extremely easy to produce at the LHC, and most of so they have large cross sections, and we have strong bounds from the LHC surface. So if I have to summarize what is the status of Sushi phenomenology right now, for sure, genetic Sushi models don't exist. Okay. Now there are pockets, there are regions, there are slightly more complicated models which are still okay, and people still work on that. But if you think what we thought like many years back, what we thought like 0.1, 0.2, 0.3, all those different study points that we worked out, those things are just gone. Okay, so that's what supersymmetry is. So let me take a slightly detour and talk about Higgs as a pseudo-number bootstrap boson and how it can solve the so-called UV sensitivity problem. Okay, so it turns out that symmetry is much easier to think of, right? Just the way we argued about the scalar case. If you impose symmetry like phi goes to phi plus constant should be a symmetry of my Lagrangian, you realize that the mu square phi square term cannot exist. Okay. So the only interaction that you can write of phi has to be derivative in nature. Okay. Now, these kinds of theories are extremely well understood, extremely well known, right? We know of them, they almost exist in nature. These are the Nambu-Goldstone bosons, right? How do they appear? It appears when a global symmetry is spontaneously broken. You get those massless modes. Now, when I say you get massless modes, because the massless net preserved is all ordered in calculation. Okay? And that's exactly because all their interactions, they have the phi goes to phi plus constant be the symmetry. And as a result of which, all the interactions are derivative interactions. So even if you quantum correct it at the end of the day, they are still remaining massless. Okay. So let me say it in this way. This is a slightly formal statement that phi is a resultant of a global symmetry G spontaneously broken down to global symmetry H. Okay, and then we typically say that the phi comes in coset of G slash H. Right. So now take an example where the full Lagrangian G is not the full symmetry, meaning that there is a part of the Lagrangian which violates G. Okay, there is a parameter, let's say G sub B, G breaking parameter that violates your capital G, the total symmetry. Okay, so if I take my GB to 0, I know that everything that I've said before works out, and I get exactly massless Goldstone, right? But on the other hand, if I turn my GB on, that's an explicitly breaking of my GB. And I know that I should expect no way that this Goldstone boson should still remain massless, because in truth, there was no symmetry group, and so there was no Goldstone boson, right? But so they should acquire mass, but they should acquire mass in such a way that when you turn GB to 0, you recover the masslessness. Okay, so that means the correction to their masses has to be proportional to GB itself, the symmetry. Right. So these examples are called the pseudo Nambu-Goldstone boson. It does have a potential, meaning that it has a polynomial, but its polynomial is such that it goes to 0 in the limit GB goes to 0. So that is what I meant by well-controlled polynomial. It has a mass square term, it has a quartic term, it has all such terms, right? But terms such that can be controlled by turning G on and off. Right? Now, why are we saying about this so confidently? Is because this is again something very well understood, because unlike supersymmetry, this actually exists in nature. Okay, this mechanism is, that's the reason why I said it is more attractive. This is exactly how, for example, pion gets masses. So as I explained before, the pion mass is your Yukawa coupling V electroweak times the lambda density. So in the limit, when you take, let's say, electroweak symmetry breaking to 0, or whether you take the Yukawa coupling to 0, such that the quark marks let me explain this in a particular manner, in a slightly mathematical manner. Consider the low energy QCD with only two flavors, meaning that up and down, they are left-handed components and the right-handed components. Okay. Now, forget about the electromagnetism right now. Okay. So that means I can think of a rotation between up and down, left-handed one is allowed. Up and down in the right-handed one is allowed. Okay. So the total symmetry is SU2L times SU2R. Actually, there are two extra U1s, but let me not get into them. Okay, that's the global symmetry. It turns out when QCD becomes strong, it spontaneously breaks this symmetry. Okay, it gives you the condensate of U bar U, D bar D. Okay, that's order of lambda QCD cube, which I have written here just F by Q. Okay, so that means if I give it a wave, then it turns out that SU2L times SU2R, it broken down to diagonal SU2 vectorial. Okay. So G in this case is SU2 square. H is in the case is SU2. Okay. The unbroken group is SU2 at low energy. The unbroken group at high energy G, that's an SU2 square. Before and after you form the concept. Okay. So the pions, since it's broken, right? So there are three generators which are broken. Correspondingly, there are three massless modes, which are the pi 0, pi 1, and pi 2, linear combination of pi 1, pi 2, what the pi pluses and pi minuses. Now, if you ask a question like how does pi transforms? How does pi transform? It transforms like the triplet, as I said before, the vectorial SU2, which we call isospin. Okay. And under the unbroken group, the coset of SU2 squared by SU2, under that, pi shifts. Okay. So for three of these, there are three different transformations. Each of these pi shifts. Pi goes to pi plus constant, pi 1 goes to pi plus constant, and so on. And this is the shift that guarantees that pi remains constant. Okay. Now, so what is my Lagrangian? Lagrangian at the end of the day is a polynomial in pi over f pi. Okay, we can write down a systematic expansion because there exists proper power counting. The power count be good as derivative over lambda, nq over lambda, and so on, where lambda equal to 4 pi f pi. Okay, so this is, for example, the Lagrangian. If you expand this guy, where u is 2i pi by f pi, if you expand this guy, the first term of it is, first non-trivial term is, first term is going to give you the kinetic term of the of pions. Okay, but the main part of it, this theory is a theory of strong QCD, right? But this theory describes pions, which here seems like rather weakly coupled, in a sense that I have a description of the pions at energies, below lambda, so that my calculations that I do, it has a systematic power expansion, and I can actually calculate. Okay, so this is the story of what pions are. Now, how do pions get masses? Pion gets masses the moment you turn on the quark masses. The moment you turn on the quark masses, explicitly you make SU12 times SU2R, because up and down no longer can rotate among each other. Okay, and as a result of which, the moment you turn on the quark masses, you get pion masses, and that's part of the reason where did it show that m pi squared become proportional to the quark mass. Okay, times amplitude. Okay, so this is what the learning is, and when I understand this, I try to impart, can I use this understanding to build a what Higgs should look like. So just like pion, the cutoff was determined by the row mass, which I said 4 pi times f pi. Okay, the pion shows up with a characteristic cell of f pi, and the pions appears in the coset SU2 squared by SU2. Maybe we can build model with the Higgs, where Higgs shows up. Higgs is a pseudo-Nambu-Goldstone boson. It shows up at the TeV scale. It has a cutoff of 4 pi f or 10 TeV, and Higgs in the coset of G/H. Now, what G shall you choose? What H you get? This is where model building comes in. Okay, this is where different kinds of models were built in. But the main point is just like in the pion case, where you get a polynomial potential at low energy of pi over f pi, you should also get a polynomial potential of Higgs, where it's suppressed by h dagger h by f squared. So I should have written an f4th here, and h dagger h by h square, h dagger h squared by f to the power 4th. Okay, so that's the comparison. And this is the story of what we call, in general, the composite Higgs picture. This is how the analog between pion and the Higgs is taken out. That some theories become strongly coupled at high energy, and as a result of which, just like you have pion and low energy pseudo-Nambu-Goldstone bosons, it's exactly in the same manner. You have the Higgses, which becomes sort of pion like a composite object, a pseudo-Nambu-Goldstone boson, and you generate its potential at low energy at a controllable manner. Okay, that's the idea. Except that this is a great scenario, but on the other hand, if you look very deep, it's still a little problematic, especially today, because you realize that if I just simply analyze this potential, okay, I expect the vacuum expectation value that you get for H, which is related to F, right? The V squared in the order of F squared times some A over B, where A are the coefficients. It's clear if A and B are the same order, meaning that let's say both of them are generated at one loop level, they both are of the same order, then you get V squared of the order of F squared. So your low energy dynamics come very, very low at 100 GeV, and this just rules down. Okay. So it's a beautiful idea, beautiful concept, but doesn't completely work. Okay. And as it happens with all theories of BSM, they start out being a beautiful, elegant picture, and at some point you realize it's so ugly that there is no way that you could say about its beauty with a straight face. Okay. So as I said, this requires you requires A to be far less than B. So a systematic way that you can get it, like if B is at 3 level, you get A at 1 loop level. If B is generated at 1 loop level, you want to get A at 2 loop level, and so on. So the game to make the composite picture clear is that what you need to do something more. What you need to make sure is that the potential that you generate over here, right after your symmetry breaking is, right after theory become composite and you get a number goes to boson, you also need to additionally make sure that if B is generated at one loop level, you don't generate the quadratic term at one loop level. Okay, this requires a little bit more research. Okay, let me spend 5 more minutes on this talk. And this is where the collective symmetry comes in. The collective, and let me say it this way. So what is collective symmetry tells you? It tells you, it's extremely clever idea. It tells you that, I'm talking about G is broken down to H. So the way collective symmetry tells you, it says that it doesn't get broken down to H at one go. There is a part of my Lagrangian where it gets broken down to, let's say, H1. There's a part of my Lagrangian, it gets broken down to H2. Only when these two parts talk together that I realize that my G is broken down to H. Okay. And that's important. In a sense that I have one part governed by, let's say, GB1, which breaks down to G2 H1. We have another part which breaks it down to G2 H2. Okay. Only when I put them together, only when they know the existence of 1 and 2 together, then only I know my Higgs is not a Goldstone boson, but rather a pseudo-Goldstone boson. Okay. It's really difficult concept. I don't know how much you get, but you can use this argument to say, like, by the same manner as I said before, the correction to the Higgs mass, so therefore, has to be proportional to both the coupling, right? Because if any one of them is 0, it becomes an exact Goldstone boson. So both of them have to be non-zero to be able to see the non-zero mass, right? And that people use that to construct the symmetry structure, the model, such that you do not generate A at one loop, even though you generate B at one loop. Okay, so that's the game people play in, and it's called the so-called the little Higgs games. Okay, but let me take a completely drastic point of view. Let me not worry about the symmetry. Let me just try to think, at the end of the day, I understand my supersymmetry in this manner that I have top going around the loop. It gives you quadratic divergence, and that quadratic divergence needs to be cancelled. So I have my stop runs in the loop, cancels it. Okay, I don't need to understand symmetry too much, but if I understand diagram, I can clearly see it. How does it work in little Higgs? It turns out the things that run in the loop are extra vector-like colored particles. Okay, and they come the theory gives the couplings in a specific manner, in the sense that if you look at the top running in the loop, this contribution is proportional to YT square. Okay, and you get it from the mass of this new person, which is again YT times subscale F, and this effective vertex between T and the Higgses is YT by F. So you put them together, the F cancels out, and this is how mechanically the quadratic divergence works. Okay, of course there's a symmetrism, but if you want to just see it in diagram, that's how it works. So prediction for these are that you have new vector-like quarks. Okay, to search for these theories, therefore, all you need to do is to think of new vector-like quark with precise couplings, so that they can cancel this divergence, even if you don't understand what the big symmetry arguments is. Okay, and that basically summarizes your little Higgs things. If I don't care too much about the rest of the stories, the way to look for the little Higgs stories, these stories, is basically to look for vector-like quarks. Okay. Now, let me spend 2 more minutes, not too much, but once you see by brute force how these two diagrams can cancel each other, you can become more creative, because you realize that in order to cancel this diagram with that diagram, okay, so this gives you YT square lambda squared by 8 pi squared, and since it's a colored, you get a factor of 3. And there also it's a loop of a colored particle, you also get a factor of 3. And so that makes you believe that, okay, this is a colored particle and therefore this should also be a colored particle. But when it comes to canceling this, it doesn't have to be colored particle. it can come from a different kind of SU3, which is not our color. Okay, so in those cases, what you see that Higgs is a pseudo-Nambu-Goldstone boson, but it's a pseudo-Nambu-Goldstone boson of a theory in which your cancellation is happening not because of some other colored particle, but rather particle charged under some different SU3. Okay, now as opposed to little Higgs, this has vector-like extra particle, but this vector-like extra particle are not vector-like undercolor. Okay. So they can't be produced it can't be pair produced by gluons. Okay, so these are so-called the neutral naturalness, that these are colored neutral particles which are coming and giving you the naturalness. Okay, so these are harder to probe, but on the other hand, these do have some visible signatures and will spend some time. But a lot of people have shifted thinking that we might have gone into the regime where the neutral naturalness probably remains one of the last few vestiges of so-called naturalness. Okay. Now, there's some calculations, but let me just avoid this. Let me try to briefly describe what these neutral, this particular model, or a particular model works. So, in those models, as we said, this is a twin Higgs scenarios. So, left-hand side is basically our standard model sectors. There is a twin sector. As I said, there is a separate SU3. So it has a separate top. It has a separate W and a Z. It has a separate bottom quark. So these things exist at a very, very high scale. But remember, these are not colored. Okay. Higgs is a pseudo-Nambu-Goldstone boson. It's light. There are other twin sector particles like B's. And so they could form a botonium, they could form glue balls, and so on. So there's an entirely rich sector of bound states that you can get into the twin sector cases. Certainly, its phenomenology is non-trivial, but highly important, because effectively this sort of looks like the portal scenario where the Higgs can decay to so-called this dark sector, the twin sector. Higgs can decays to those B's by small amount. These B's form the bottomonium, and they can decay further at low energy, depend on specifics of the theory. Okay, some of it can come back to the standard model, and what you would get at the end of the day are displaced vertices and so on. Okay, these are highly interesting things, and in fact, these are one of the good signatures of what should I say? Motivated signature of displaced vertices. If you're looking for displaced vertices and long-lived particles, this is one of the very, very few cases where you could motivate yourself. That there is some theory which wants me to be displaced. Okay, rather than just because I can write down a short, small coupling, I'm writing down a small coupling. Okay. So 24. Can I have 5 more minutes?
Yes, please go ahead. Please go ahead.
Okay. So here, let me go back from this, last 40, 50 years of research, and let me think like, last 10 years, what increasingly more and more people, how they started to think about it. Okay. It's very clear there is nothing, no low-hanging fruit anymore. No. So if new physics exists, it's very likely that light physics has to be non-trivial in a sense that it cannot be straightforward. It has to hide. Okay, it's like God is playing with our minds so that you can hide yourself properly. Okay, but the possibility there exists in new physics, that new physics is probably in a very, very heavy state, and then you ask yourself, there are too many scenarios, and is it worth looking for specific BSM scenario? Okay, probably not, and that's the reason why people want to think in terms of the effective field theory way of looking at the BSM scenario. Okay, as I said, I'll take 3-4 minutes to explain the concept of EFT, and maybe then I will briefly describe what the EFT is. Okay, so what's an EFT? So there are many kinds of EFT. There's no global definition. I try to come up with something simple, meaning that I look at only a limited set of observables to explain that limited set of observables, nothing else. I write down a theory with a definite set of degrees of freedom. Let's say a limited set of observable here I define for all the observable where energy is less than lambda. I take that set of observable to describe those observable. I take the fields, a limited set of fields, let me call this phi lambda, and I construct a Lagrangian such that I can explain those limited set of observable using my degrees of freedom. Okay, and this is the collection what we call an effective field theories. Okay, now what is effective about it is that if you use that thing, use that setup to calculate some observable which was not included into your list of limiting set of observables, then you get poor answers. Okay, you force yourself, you're going to get poor answers. As opposed to what a full theory is, in which all the observables that you take, in principle, you can calculate, and all observables you can use the same theory to calculate and get an answer. In principle. Okay. Now let me just what I said in word. Let me describe a full theory. Let's say call the descriptions. The degrees of freedom are phi's. Its interaction is Lagrangian, and the observables. Let me say are O's. And EFT I wrote down as a limiting set observable phi lambda. It has a different Lagrangian lambda LEFT. It has a different set of, it's a subset of these O's, which I said that I'm going to explain. Okay. Now, by construction, these two are such that O lambda, when those observables, whether you calculate in the full theory or whether you calculate in the EFT, they should all yield the same answer. Okay. They should have all the answers that your experimentalists get. Okay. And that basically gives you a way, for example, to, if you know the full theory, to determine what the EFT is. Okay, and that procedure is broadly what's called matching. Okay, let me give two simple examples. First one we know, like the muon decay, right? The full theory, again, standard model. We know how muon decay, it decays via a W exchange. Okay, they can calculate what the width is. I can take my EFT, which involving only muon, neutrinos, and electron. Okay, and I write down a dimension 6 operator, and I demand that this gives me the rate, at the same rate at which muon decays in the full theory, which is my experimental number. Okay, so then you realize that I get an effective field theory where my phi lambda, mu, electron, neutrino, which were also subset of my original Lagrangian written in terms of that. Okay, so example 2 is slightly different. Instead of muon decay, you're looking at kaon decay. Okay, so your EFT doesn't have quarks or gluons, but it has kaons and pi's. Okay, so degrees of freedom are slightly different. But again, it has a dimension 6 operator, and both the theories I can use. But if I need to calculate something on kaon decays, I will take this particular theory. Okay, use this condition to determine certain aspect, and then we'll take this theory to determine something. Okay. The reason I gave this example is, do not think always in the mind that the degrees of freedom with which you are writing your EFT has to be the same as your full theory. They could be different. Okay, so now let's come back. Now, clearly, when you try to say I'm model independent, I have a problem, because like if I take the Sushi scaled up supersymmetric theory, and I want to write an EFT theory of that, if I take a little Higgs theory, scaled up little Higgs theory, and I want to write an effective theory of that, they are two different effective field theories. No? By construction, they have different observables, so the effective field theory should match these different observables, so they are different. Okay. So how do we different? So the usual expansion that we do, you write a set of operators, you match your dimensionality so that the whole thing has a mass dimension 4, and you write the various coupling constant in front of them, which are the Wilson coefficients. So effective field theory or specific BSM scenario, it just tells you that some of the C's are 0, some of the C's are suppressed, and there are various non-trivial relationships among various C's. Okay, so that's an effective field theory or specific scenario. If you take an EFT for a different scenarios, you'll find a different set of Wilson coefficients which are 0. You'll find different connecting relationships between different Wilson coefficients. Okay, so what you do then? Well, you just take this Lagrangian that you have constructed, which is a systematic expansion, and forget about these constraints. You forget that there is something that's vanishing. You forget that there exists non-trivial relationships. So in a sense that you are now scanning over all BSM scenarios, okay? And that's how you can construct yourself a model-dependent model independent wave. Okay, last slide. So the two parallel way that we construct the EFTs. One is an expansion around the electroweak symmetric vacuum. The other, we construct EFT around electroweak breaking vacuum. So when I say around symmetric vacuum, that means the full symmetry that I take into account while considering this expansion is there is a color, there is electroweak, there is hypercharge, and so on. As opposed to the other case, if I do electroweak breaking vacuum, I only have to think care of the color and the electromagnetism. Okay. The Higgs degree of freedom in two cases are different. In one case, you use the electroweak doublet, and the other case, you use the 125 GeV scalar. For 125 GeV scalar, the expansion is a polynomial in H over V. And for the other case, it's a polynomial in not just Higgs over lambda, fields like GQ bar over lambda cubed and so on like this. Okay. And here's an example, like this is the Yukawa coupling, and you add an extra operator, which is H dagger H by lambda square. So that's how you do by a next term in your SMEFT. If you want to do the same term in HEFT, you have an U bar U, which is the mass term, H over V. What you do, you simply add H square over V square, but this is the 125 GeV directly. Okay. If you want to do phenomenology with this, then you have to still expand this around P plus H, and from that you have to write what the 125 GeV guys term is. Okay, so these are the roughly two terms. There's a short term to show. There's a slide. When you put it, you can check it. This is just to show that the kappa modifier, for example, the one that we are fond of, that via which we often give our results, is how it simply involves, like, there's a direct connection between EFTs and the kappa modifiers and so on. Okay, so let me summarize. It took really long time, but as I said, I only managed to cover a few BSM scenarios, and that too in a extremely pedestrian style. I couldn't just get into detail because the literature is so vast. Okay, but I hope that it gives you some understanding of why and how we have invested a substantial amount of time in the last 2 decades after Higgs. Even though till now we don't have any direct evidence of BSM so far. Okay, thanks a lot.
Thank you, Tuhin, for a nice talks at the pedagogical level to the students. It's already late, but let's open the platform for a couple of questions from outside. Just anybody can raise the hands.
Nice talk to you.
Rajiv, you had a complaint?
Maybe he left.
No, I'm around. I was just hoping that the students might be having some questions, so I was waiting for them to ask first. I had a comment, perhaps question, but if you want to go there first, then go to that Troy example that you took in the beginning.
Which one, the toy model or the pioneer?
Yeah, no. Previous slide, yeah. So supposing I say that the masses, the fermion mass and the scalar mass are fixed, then yes. What happens?
No, they are fixed.
No, then what was this decoupling? What was this decoupling where, yeah, see, this fermion mass is actually fixed to be the one which we know from the observed world. So the maximum I get is top quark, which is 175.
No, my feeling is that when I wrote this, let me think of it like this is at, I don't know, 10 to the power 10 GeV. Put that mass over there.
So this is an hypothetical fermion which doesn't exist.
Yeah.
So that is the question. If I actually did this calculation in the standard model,
yes,
then I don't have this problem.
No, you don't have this problem.
So to really say that the fermion mass is the source of,
has no problem.
No. So to say this, that the fermion mass is the source of UV mass scale is not the right, as much as imagining that there exists a heavy mass particle, fermion or boson. That is the source of the UV sensitivity.
Yes.
So in that sense, standard model doesn't have this UV sensitivity.
No, that's exactly what I was trying to tell you. That if you take the standard model as an UV complete theory, okay, you take that approach that, okay, I have, God has not given anything, okay, above this scale, I do not think you have a problem. You don't have this problem. This is only exists if there exists heavy particles.
No, you don't really have to invoke God. Even experiments will help you. Z decays have told you that the number of generations is 3. And from that, you already know what it is. Now, you could always say that there exists a mass, a particle, a doublet, which is at 10 to the 17 GeV. But that's something that you are imagining. It doesn't, there is no reason that it should be there or it should not be there.
So there are two different issues over here, right? So the first issue as the UV sensitivity issue, right? Let's forget about the Higgs and what happens. The UV sensitivity issue is this happens whether you have at high scale, whether you have a Fermion or whether you have a scale. Okay, so that's a different issue. Now the question is that in the standard model, what happens in the standard model? Should I actually worry about this or not? If the standard model is the ultimate truth, then I don't think there is an issue.
So if you see a proton decay,
I would be very
only there is a problem. If you don't see a proton decay, then there is no problem.
If I see a proton decay, there is a definite problem. Okay, if I do not see a proton decay, there is no definite problem.
And this is what I think you need to really decouple from the fact that the hierarchy problem or this ultra UV sensitivity really arose in the grand unified theories where proton decayed, and all the experiments are showing that proton doesn't decay. Unless you assume that the proton decay exists at some scale that you don't always beyond the experiments, there is no way you can argue for this hierarchy.
No. Rajiv, we are having this conversation since we joined, right? Day4. We probably have this conversation for a very, very long time. No? So what I was trying to hear, you're trying to think whether there exists a God scale or not. Right? This is what you are bringing up with the question of proton decay. So that if you see proton decay, you know that there's definitely a dynamics that is not captured by the current understanding of our Lagrangian. Okay. In order to do that, you need to introduce a new degrees of freedom at a high scale, something like this MH scale. And once you have it, then you definitely have a problem. Okay. So when people say that we have UV sensitivity, right? There is the word usually comes that if there exist heavier states, okay, then we have this problem. This is the caveat. That's why people use this language. Okay, now there are two things. Many of the things we don't completely understand, right? So first of all, when I say standard model is the only part of my theory, right? So that means I do not exist in my nature. Let me think of nature, and let's say there exists no gravity, only these three forces, right? Even in these three forces, I know that the story is not complete. In the sense, the story is not complete in the sense that there is a hypercharge which runs above, right? And there is no definitive answer to how to regulate that theory, which becomes strongly coupled at UV scale, right? So don't completely know the UV of standard model completely. So let's be very practical here, right?
Okay, go ahead. I was just curious if you can take it offline. Actually,
okay,
we are getting late by 10 minutes. So yeah, I see no other hands there. So thank you, Tuhin. Let's thank Tuhin on behalf of organizers for nice talk.
Thanks a lot.
Thank you.
I hope it was helpful.
Yeah.
Yeah.
Thank you.
Thank you. We'll go